So here are two problems that are in what I would call an accumulation style. When we talk about our different categories of free responses, accumulation is one of those categories. So we're going to do the ones that were from 2015 and 2014. So 2015 first. It reads, the rate at which rainwater flows into a drain pipe is modeled by the function r. So some important things to recognize here in this first phrase. We want to make sure we recognize that we are looking at a rate or a derivative. If at some point I need a derivative for some reason, I've got one. And that this derivative represents the rainwater flowing into a drain pipe. And I don't know how to draw a drain pipe, so that's going to be my drain pipe here. And so if I were to depict that, that then would be my R of t. R of t is going into the drain pipe. It's a positive idea, right? Filling the drain pipe going into. And it's modeled by this function here. We notice then that we have some units which are important, cubic feet per hour. So I know I'm talking volume because of that cubic feet, and then hour would be my time element, where t is measured, and sorry about that, that space obviously should be after the d, but is measured in hours. And then we have a window here to consider, 0 to 8. The pipe is partially blocked, allowing water to drain out the other end of the pipe at a rate. And so again, we want to take note of the fact that we are once more talking about a derivative here. And this time, this d of t is how we are draining out of the pipe. And so if I were to depict that in my picture up here, d of t would be the negative idea leaving the pipe. Which also then brings to mind the fact that we know what's happening inside the pipe. If r goes in and d comes out, then r minus d would represent what was inside of the pipe. And if you struggle a little bit with that kind of conceptual idea, then maybe give it a little bit more of a concrete concept. The idea that if you had 7 go in and 3 come out, well, how much would be left inside of the tank? 4. 7 go in, 3 come out, 4 left inside. How did we get that? Well, we did 7 minus 3, which is that r minus d. Same units for d, which makes sense since this is the amount of water leaving, so volume, and then per hour for time. Same window, 0 to 8. We would want to make sure we considered the fact that they were the same window. If for some reason this was 0 to 8 and this was, say, 4 to 8, then if we were talking about some time between 0 and 4, we would only consider the element or the function that had a bound 0 to 8. Not the 4 to 8 yet. But because they do have the same boundaries there, 0 to 8, we know that both are at play the entire time. R and D are happening simultaneously throughout our time interval of 0 to 8. There are 30 cubic feet of water in the pipe at time t equals 0. For me, this brings to mind x sub a plus the integral from a to b. Why are they taking the time to give me a location if that location is not going to in some way, shape, or form be important later on? Okay? So then we're on to A. A reads, how many cubic feet of rainwater flow into the pipe during the 8-hour time interval 0 to 8? So this question, how many, how much, what's the total, what's the quantity, anything along those lines, that implies an integral, right? That's what an integral does. An integral finds area. An area is a total. And so when they're asking us, how many, this would be the total cubic feet of rainwater flowing into the pipe. Okay, so if I were to solve A here then, this is A, I'd be finding an integral, and then it's flowing into the pipe, so I'm just going to use my R of t. And then my bounds are 0 to 8. Because that's what they asked during the 8-hour time interval 0 to 8. So then if you pick up your calculator and you plug this in doing Math 9 or graphing R and doing second calc integral or however it is that you solve your integral, you're going to find at the end of that you're going to get about 76.570. They didn't ask us specifically for units here, but they did indicate how many cubic feet of rainwater, so I do know that this is feet cubed. In addition, I know because I took an integral of R, and R was cubic feet per hour, so that integral would undo that per hour, sending me back to cubic feet. Okay. We are now on to B. B reads, is the amount of water in the pipe. So now we're talking about some sort of R minus D relationship here. Is the amount of water in the pipe increasing or decreasing at time t equals 3 hours? Well, what does it take for a function to increase or decrease? It means that your derivative is either positive or negative. Okay, well, what's the derivative of in the pipe? R minus D. That's what R and D were. Remember, R was a rate and D was a rate, meaning these are already derivatives. In essence, what they're asking me here is, at t equals 3, is R minus D positive or negative? Because then I would be able to know whether my function of the amount of water in the pipe was increasing or decreasing. And so then that's what part B involves. We're going to go ahead and figure out, well, what is R of 3 minus D of 3? And you're going to pick up your calculator, because this is a calculator problem, so you'd be able to use your calculator. And you're going to plug that in. And when you plug that in, you're going to get that R of 3 minus D of 3 is negative 0.313632. Okay? Which is less than 0. This is negative here. Okay? And so our function, the amount of water in the pipe, is decreasing at t equals 3. And then they say, give a reason for your answer, meaning we need to be able to articulate some sort of rationale for how we knew. For me, I'm going to write because R of 3 minus D of 3 is less than 0. Okay. Now we're on to part C. Part C reads, at what time t between 0 and 8 is the amount of water in the pipe at a minimum? Justify your answer. Okay, so if we were trying to find a relative minimum, this would be a change in f prime from negative to positive, and where f prime equaled 0. So we might be wanting to consider f prime equaling 0, or if this were an absolute minimum, we'd want to consider those relative minimums as well as our two endpoints. So for me, I'm going to go ahead and consider the absolute minimum, because that'll help me identify where a minimum would be. And so where would my absolute minimum potentially be? It could be, like we said, at an endpoint, so that would be at t equals 0 or at t equals 8, or this could be at a relative minimum. Okay, we are again talking about the water in the pipe, so again I'm going to be looking at R minus D here. If I took my calculator and I graphed R minus D and I put that into my Y1, I'd be able to ascertain that there is a 0, both at 0 actually, and then again there is a 0 at 3.27165, or 166 if you round it. So you're going to find that there are two zeros. Well, that second 0 there, because we've already taken into consideration t equals 0, the other one is at 3.27165 or 66, because it is 658 there, so whichever one you prefer. And again, we found this value by considering where, I'll put it off to the side here, where our R minus our D equals 0. And then our endpoints, of course. Okay, so then the question is, well, which one of these is actually our minimum? Which one of these is actually the lowest point? Well, to do that, I need to plug it into my original function to determine who's the highest or who's the lowest in this case. Well, I don't have an original function. I have derivatives. And so, well, how do I get an original function out of a derivative? Well, that's where this desired position formula comes from, right? My x sub a is going to be 30, we'll do it on this one, plus my integral, my a is the time corresponding to that position, which is 0, and my b is the time at which I'm trying to find the position, and that time for this bottom one is this 3.27166. And then our velocity is going to go inside of there, or I should say our derivative is going to go inside of there, which is our R minus D. Since we are talking about what's inside the pipe, they're both going to go in. And you do that for each of them. We do the 30 plus 0 to 8 of r minus d. And then obviously at t equals 0, we already know that that's 30. They told us that. Okay? And so then if you pick up your calculator and you plug this in here, at time 8, you're going to find that your position is about 48.5436. And that your position at our 0 here of 3 point, etc., our position here is going to be 27.964. And so then as I look at these, well, which one is where my minimum is? My minimum is located at t equals 3.271. It's the location of a minimum. Now, if they asked me what that minimum was, I'd answer it with the 27 number. But because they asked me to find the minimum, where is the minimum, I'm just going to answer with the t. Okay, and so now we are on to part D here. Okay. Part D reads, the pipe can hold 50 cubic feet of water before overflowing. So again, we're talking about inside the pipe, so if I need a rate, it's going to be R minus D. For t greater than 8, water continues to flow into and out of the pipe at the given rates until the pipe begins to overflow. Write, but do not solve, an equation involving one or more integrals that gives the time W when the pipe will begin to overflow. Okay, what is that expression that involves an integral that gives me a time when the pipe will begin to overflow, that takes into consideration a particular position, that place where we reach 50 cubic feet of water? That equation is our desired position formula. My x sub a again is 30. My a is 0. My desired time in this case, we're going to call it W, because I don't actually know what that time is, but I'm trying to find it. And this position, we know what this position is going to be. This position is going to be 50, because that is the point where the pipe begins to overflow. And then I'll leave it there, because it just says to find, to write, but not to evaluate. Okay? Okay, so you've heard me walk through one. My challenge to you on the next one is try bits and pieces of it on your own. Maybe pause the video, see if you can do a part of it or part of a part of it or something like that. Starting with here at the beginning, I would recommend pausing the video and just process that initial paragraph. Identify what's important in this paragraph that you might need to take into consideration later on. Okay, so Calculator 2014 problem here reads, grass clippings are placed in a bin where they decompose. The fact that they are decomposing does to me communicate a negative idea. I may or may not know what the negative is, but again, decomposing is a negative directionality. We have a window for 0 to 30, so I'm not going to consider anything outside of that window. The amount of grass clippings remaining in the bin is modeled by this function. And so we want to take note, this function is the amount of grass clippings inside of the bin, meaning this is not a rate. A of t is not a derivative. A of t is an actual original function. It measures the amount of grass clippings in the bin. A of t is measured in pounds, so we're looking at pounds here, and t is in days, and so we've got some units. Okay. A reads, find the average rate of change of A of t over the interval 0 to 30 and indicate units of measure. So, average rate of change. There are a couple of different ways you can process that phrase here. Me personally, I do it this way. Average is 1 over b minus a times the integral from a to b, and then rate of change of a. Well, rate is derivative of a. The derivative of a is a prime. And so that is the setup of my average rate of change, b and a being 0 and 30. So So I'm going to have 1 over b minus a times the integral from a to b of the rate of change of a. Okay. Well, nice thing about a derivative and an integral is they are inverses of each other, meaning they'd cancel each other out. So this integral would undo the derivative, the prime in this a prime, sending me back to just a. And if I plug in my upper, a of 30, minus plug in my lower, a of 0, over 30, I now can use my calculator. This is a calculator problem. I can plug 30 into my a equation, and I can plug 0 into my a equation and get what those two numbers are. The other way to process the problem, like I mentioned at the beginning of this, I said that there's a couple of different ways you could. You could jump right to this point. This is f of b minus f of a over b minus a. This was my b minus a originally. You can jump right to that point as long as you are finding average rate of change. If it is just the average value of the function, we can't jump right to that point unless we do know what the integral of our function is. But you want to be careful about when you use that idea. Okay? Or the other way you could do it, with the same initial setup here, is rather than thinking through this idea of the integral undoing this derivative, I could actually find what a prime is. This would be an a to the u rule here. If I were to find the derivative of this function, this is a coefficient, so it'll just hang out, and we have a to the u times u prime times the natural log of a. And you could actually calculate what that derivative would be. So this would be 6.687 coefficient, so hanging out, and then a to the u times u prime, so that's times 1, because the derivative of t is 1, times the natural log of my a. And then I could just math 9 this for 84s, or graph it, or however it is that you calculate your integral, and you could let your calculator do the work for you. Whichever method you choose, whether you come from this spot or this spot, you're going to find that you get negative 0.197 or negative 0.196. I did round here. You also could truncate. And then they asked us for our units of measure. Well, I just found the average, so kind of that middle representative value. It's not actually straight in the middle always, but that would be a median. But the kind of representing the majority of your data points. So the average rate of change of a. So this is a number that represents the majority of the rate of change of a. Well, how do I express that unit? This is the derivative of a, and since a is pounds, the derivative of a would be pounds per day. Okay. And we're on to part B. Part B reads, find the value of a prime of 15. Using correct units, interpret the meaning of the value in the context of the problem. So we're finding a prime of 15. Again, you have a choice to make here. You could actually find what a prime of t is, just like we did up here in part A, and plug 15 into that. Or it is a calculator problem, so you could calculate your derivative in your calculator using Math 8 for 84s, under Calc in the home screen for 89s, or you could graph the function and calculate your derivative in the graph piece. However it is that you are more comfortable. But you're going to find, whichever route you choose, that you get a prime of 15 is negative 0.164. Or this, again, was rounded, so negative 0.163 would also work. And then they ask, or we are asked to interpret the meaning of this value in the context of the problem. We do want to use correct units here. Okay, so our negative 0.164, its units, since this is a prime, would be pounds per day. Okay, what is this? This is the rate, because this is a derivative, at which my A of t is changing. A of t is the amount of grass clippings in the bin. So the rate at which the amount of grass clippings in the bin is changing at t equals 15 days, since this was a prime of 15. You also could talk about the amount of grass clippings decreasing or decomposing, although if you do that, make sure you don't include the negative. That would be 0.164 pounds per day is the rate at which the amount of grass clippings in the bin is decreasing, since decreasing implies that negative idea. C. C reads, find the time t for which the amount of grass clippings in the bin is equal to the average amount of grass clippings in the bin over the time interval 0 to 30. Okay, so if we were to parse this sentence up, find the time t, so we're going to be solving something for which the amount of grass clippings in the bin, well, that's A of t, is equal to the average amount of grass clippings in the bin. Well, average is 1 over b minus a times the integral from a to b, amount of grass clippings. Well, that is A of t. And then my b and a are 30 and 0 again. So this is 1 over 30 minus 0 times the integral from 0 to 30 of my A of t. Okay. You now need to solve for t. Again, there's a variety of options. One that you might choose would be to subtract this expression over here over to the other side. This could allow you to calc a 0. Now, some calculators might move pretty slowly if you calc a 0 here. Let me write equals 0, sorry, because we have subtracted this over this other side, so this would be equals 0 here. Some calculators might process this rather slowly, and so you could actually find what that value is, do math 9, and calculate what that number is, and then plug A of t minus that number in to calculate 0. Or again, however else, or in whatever other way you typically solve a problem, you're going to solve for t. And so we have t equals, and then you're going to get 12.415. And I believe, if I remember correctly, I think I rounded this one as well. So 12.414 would be the truncated version. Okay, last but not least, we have part D. Part D reads, for t greater than 30, L of t, the linear approximation to A at t equals 30. So what is this asking us? This is asking us for our tangent line equation at t equals 30. Okay. L of t then would be our y. So we'd have our y minus our y1 equals t in our tangent line equation would be our x, m times x minus x1. And we're finding this linear approximation at t equals 30. We're told that this is a better model for the amount of grass clippings in the bin. We're going to use this model, once we have it, to predict the time at which there will be 0.5 pounds of grass clippings remaining in the bin. So we're going to again be using this, this model to find 0.5 pounds of grass clippings. So ultimately, where am I going to be plugging this into? I'm going to be plugging this into my y, or into my L of t. And so I'm going to make sure I keep that in mind. I'm not going to be plugging this 0.5 into t here, or into x, because this is not a time measurement. This is an actual amount measurement. This is going to be plugged into my L of t or my y, not into my t or my x. Okay? But before we can get to that point where we plug in, we do need to find these two pieces. What is y1 and what is my slope? Okay? Again, it's a calculator problem, so personally, I'd probably graph my a of t, and then I would trace to get my y1. Trace to t equals 30 and determine what is that y coordinate. The other option is in your home screen. You could just do 6.687 times 0.931 raised to the 30th. It's not like that would take that long. It's just, if you wanted my personal opinion, I'd probably use the graph myself, but you can plug in. And you're going to get that your y1 here is 0.7829. And there was a little bit more than that too. I believe it was 2.8 or 2.7, something like that. I think it was 2.8. And then your slope, again, you have a choice. If you're in your graph screen already, I'd do second calc derivative myself to find my slope and then plug in 30. Or you could actually find the derivative of a of t like we've already done in part A up here and plug, oops, make sure that's on the screen, like we did in part A up here, and you could plug 30 into that derivative function here. Okay. Regardless of however you do it, whether it's in your graph screen or doing it by hand, you're going to get negative 0.055976. And so then that's my function, y equals negative 0.055976. Times x minus 30 plus 0.782928. Okay. And now we're going to use it. Remember what we said. Our 0.5 here is our y, or our L of t, so we're going to be plugging this in to here, not to here. So we're going to do 0.5 equals our negative 0.055976. And then they do want us to show our work for solving this. It's kind of the ending of the instruction there, so we're going to go ahead and subtract this piece over. So we're going to have 0.5 minus our 0.782928 and divide over this number here. Okay. Then our last step is going to be to add this 30 over to the other side. 782928. Okay. And personally, I'd probably leave it there. You could though, because it is a calculator problem, pick up your calculator, plug it into your calculator, and you'd get, it's about 35.054. Okay. So then those are two accumulation problems.